Okay, welcome to part 3, the real case hardening 101. Now, I'm going to apologize in advance. Occasionally I'm going to be looking down at my notes. I have 5 pages worth of notes here, and I don't want to leave out any of this information. Now, there are a couple different methods you can use to case harden. The one we used in this video is called pack carburizing, and there are many different recipes that you can use for pack carburizing. There are commercial compounds, which are, I guess you'd just call them applied case hardening compounds. And then there are methods in industry that I have no knowledge of. Okay, so recipes for pack carburizing. Now, we went over Tums, and Tums is a pre-combined carbon source and a chemical, which is calcium carbonate, that aids in carbon absorption. A tum will expand to about 3 times its size and heat, and this is good and bad because it can fill any gaps that are left around your material, and bad because it creates pressure, more pressure. It tends to, if you ever lit those firecracker or them firework snakes, them black snakes, and they just grow, that's what this Tums does. In all the gaps, it'll make a snake out of it as it's expanding, and like I said, doesn't smell the best because it's burning sugar. Okay, the next recipe is just crushed charcoal. This is some charcoal that I put through the blender this morning. Now, the burning some charcoal in the container turns the oxygen into carbon dioxide, which allows the carbon absorption. Some of the charcoal will burn because of the oxygen sealed in the container. But once all that oxygen has been consumed and turned into carbon dioxide, the charcoal will stop burning, and the charcoal that burns will burn off before any scale forms on your piece. So you don't got to worry about scale forming on your piece, inhibiting carbon absorption. Now, this is the least effective method because you don't have anything to aid in the absorption of carbon. All these other recipes have an aid, and basically that frees up the carbon in the pack to do its thing, absorb into the material. Whereas just charcoal by itself, it's having to pull double duty. Okay, the next is just crushed charcoal with kosher salt. Now you want to mix it in a 60-40 ratio by weight of charcoal to salt. Now it sounds like a lot, but you're going to have a mound of charcoal and a handful of salt because salt is so much heavier than charcoal. Kosher salt contains an anti-caking agent that is yellow prussiate, which is sodium ferrocyanide. And that is what's going to aid in the carbon absorption here. Many case hardening recipes, both new that I found on the internet and old that I found in my books, mention yellow prussiate as an ingredient. Don't freak out about using it because cyanide. Ferrocyanides are rather harmless, especially compared to other salts of cyanide. Okay, the next recipe is crushed charcoal with baking soda, sodium bicarbonate. Now, this is basically the same as the Tums. We are just switching our carbon source from sucrose to charcoal, and our aid from calcium carbonate to sodium bicarbonate. Now, this mixture should not expand. The only expansion that should take place inside the container, and this is true for all these methods, is the gases inside the container when they expand due to heat. Okay, the next is the commercial case hardening compounds like cherry red and caseinate. They use harsh toxic salts that allow rapid absorption of carbon into iron. I find when you use them as directed, they don't penetrate very deep, though I don't think they're designed to penetrate deep. They're just designed to give you a quick, hard surface for wear resistance. Okay, in my small library of blacksmithing books, here in the Blacksmith's Cookbook by Francis Whitaker, he references case hardening as tooling 4 times in this book, and he gives you a recipe. It's a single ingredient recipe, but it's a toxic salt. And in Practical Blacksmithing, and this is the 4 volumes combined into one Practical Blacksmithing, so it's the one big book and not 4 small books. There are many references and recipes of case hardening in this book, and I'm going to read you a couple of the passages in here. Case hardening steel or iron. I think the best and simplest method of case hardening iron is to use prussiate of potash, the yellow prussiate that was in our kosher salt. It is a yellow substance that comes in the shape of flaky, shining flat lumps. Pulverize it until it is fine as flour. Heat the article to be hardened to a deep red and put on the potash just where you want it to be hard. Then put it back in the fire, heat it to a deep red, and plunge into cold water. To harden steel. A very fine preparation for making steel very hard is composed of wheat flour, salt, and water. Using, say, 2 teaspoonfuls of water, 1/2 a teaspoonful of flour, and 1 of salt. Heat the steel to be hardened enough to coat it with the paste by immersing it in the composition, after which heat it to a cherry red and plunge in cold, soft water. If properly done, the steel will come out with a beautiful white surface. It is said that Stubbs files are hardened in this manner. Now, using my knowledge on this subject, wheat flour, salt, and water. Okay, the salt is to aid in the absorption of carbon. The wheat is both a binder and a carbon source, and the water is just to make it a paste, so it'll stick. He can form it onto his iron. Case hardening. Case hardening consists in the conversion of the surface of wrought iron into steel. The depth to which this conversion takes place ranges from about 1/64th to 1/32nd of an inch. The simplest method of case hardening is to heat the work to a red heat and apply powdered prussiate of potash, again yellow prussiate, to the surface. In this process, the secret of success lies in crushing the potash to a fine powder, rubbing it well upon the work so that it fuses and runs freely over the work, kind of like when flux flows on your work. Then the latter must be quenched in cold water. It is essential that the potash should fuse and run freely, and to assist this is a spoon-shaped piece of iron. The concave side to convey the prussiate of potash, and the convex side to rub it upon the work. If by the time the potash fuses, the work has reduced to a low heat to hardened, so it basically forms a crust, it should be placed again in the fire, the blast being turned off, and worked over and over until a light blood red heat is secured, and then quenched in quite cold water. Work case hardened by this process has a very hard surface indeed, and appears of a frosted white color, resisting the most severe file test. Since, however, it is an expensive process, and is unsuitable when the article is large and of a regular form, what is termed box hardening is employed. This is another name for pack carburizing. This consists in packing the articles in a box and closing the case hardened materials. The box is made airtight by having its seams well luted with fire clay. The case hardening materials most commonly used is bone dust, a layer of which is first spread over the bottom of the box. A layer of the pieces to be hardened is then placed in the box, care being taken so to place them that when the bone dust is consumed, the weight of the uppermost pieces will not be likely to bend the pieces below them, or to bend their own weight, and it follows that the heaviest pieces should be placed at the bottom of the box. A better material, however, is composed of leather and hoof cut into pieces of about an inch in size, adding 3 layers of salt, the proportions being about 4 pounds of salt to 20 pounds of leather and 15 pounds of hooves. Adding about 1 gallon of urine after the box is packed. The box lid should be faceted down and well luted with fire clay. It is then placed in a furnace and maintained at a red heat for about 12 hours. When the articles are taken out and quickly immersed in water, care being taken to put them in the water endways to avoid warping them. Work that is thoroughly box case hardened has a frosted white appearance, and the fanciful colors sometimes apparent are proof that the case hardening has not been carried to the maximum degree. These colors are produced by placing charcoal in the box and heating to a lesser degree. So I think he's talking about color case hardening there. Case hardening plan 2. One of the prime requirements in case hardening is that the article shall be well polished. If the iron is not quite sound or shows ash holes, it is hammered over and polished again. The finer the polish which is imparted to the surface, the better the results will be in case hardening. The articles are next embedded in coarse charcoal powder in a wrought iron box, which should be airtight. After the articles have been thus prepared, the box or pipe is exposed for some 24 hours to a gentle cherry red heat. Sometimes a flue steam boiler is used for this purpose, or the heat may be obtained in any other place where fire is maintained uniformly. By exposing the articles to the heat for the period named, a hard surface of about 1/8 of an inch in depth is obtained. If so much time cannot be given to the operation, or if deep hardening is not required, the articles may be embedded in animal charcoal or a mixture of animal charcoal and wood charcoal, exposed for a much less period of time. 4 or 5 hours will be found sufficient to make a good surface of steel. Now, in this practical blacksmithing book, I didn't read all the case hardening methods in here, but there are very many instances where they use a name like aquaphorus for a chemical that is no longer in use. A quick Google search of the word will give you the chemical name and its properties. So in the last video, when I was showing you the broken knife pieces that I had polished and etched, I first forgot to explain the colors of iron. Now, iron will look different colors depending on whether it's cold or just exposed to an acid. And we aren't counting tempering colors in this talk because it has nothing to do with it. Now, say we have 2 bars of iron, one of low carbon steel or iron and one of high carbon steel. We get them both up to non-magnetic critical temperature, 1500 degrees Fahrenheit or 816 degrees centigrade, and we quench them in water. Now, we quench them in water because it's violet and some scale is going to pop off. Now we pull out the low carbon bar and we look at where the scale popped off, and it's showing the bare metal. It's going to appear very dark, almost black. And we look at the high carbon piece and it's going to appear bright, almost white. This is due to the carbon content in the metal, and in the high carbon piece, the formation of martensite. If you want to know more about martensite and the phases of steel, I highly recommend you check out Sam Town's video on the subject. Now, we polish these pieces clean and we expose them to an acid. The opposite is going to be true. The high carbon steel, due to the carbon in it, is going to etch dark, almost black. And the low carbon is going to etch bright, almost white, because there isn't as much carbon. And the medium carbon steel will be in the gray range, the color of gray being brighter or darker depending on the carbon content. Talk about carbon sources: charcoal, wood, bone, leather, sugar. There are many others. It really doesn't matter what you use, because at the end of the day, carbon is carbon. Now, however, that being said, what you make your carbon out of could also aid or detract from its suitability for use in a case hardening compound. Let's take bone as an example. Bone can be turned into carbon, but it also has lots of calcium in it. Not calcium carbonate, just calcium. That doesn't do anything for the case hardening process, and it's taking up space in your container where more carbon could be. Okay, now you can fully carburize a piece, make the carbon content homogeneous in a piece of iron with enough time and heat, although this is usually very impractical. Now I've drawn a simple chart here. Time on the bottom, heat on the side. And basically, the more heat you have, the less time you need for your carburizing. Now you see the chart goes up and then down. That's because the forge has to heat up. Your campfire has to heat the pieces up. So that's gonna eat up some time. But once you get up to a really high temperature, the graph starts going down because the iron is more accepting of carbon due to the high heat. Case hardening works better the lower the carbon content of something is, due to the affinity of carbon to go from high concentration to low concentration. Basically, it means it's easier to start low and go high than it is to start high and try and make it go higher. It's possible, it just takes more time. Okay, we're going to talk a little bit about the chemistry of case hardening. Now, I'm not a chemist, so I will give you the layman version, how I understand it. Now, depending on the method used, carbon monoxide or carbon dioxide is produced with an excess of carbon thanks to all the carbon we packed into that container. The excess of carbon is then diffused into the metal, the rate of which is controlled by temperature and time. In the case of commercial case hardening compounds, the toxic salts combine with the other ingredients at heat to deposit the carbon in the mix into the metal surface. Okay, we're going to talk a bit about the absorption of carbon into different shapes and what you need to think about in your tool design when you are considering case hardening it. Now, remember, carbon comes in all sides. So, the wider it is, the longer it's going to have to sit for the depth of case harden that you want. You can manipulate this by starting to skinny up the shape. Now, you gotta be careful on this because it poses a problem. Like our knife, we'll draw these triangles pretty well, represent the cross section of the knife that we made and did the break test and etch on. So at the blade to ricasso area, I was in no danger of over carburizing my piece and creating brittle, worthless cast iron. In the middle, still no worry. At the start of the distal taper, or a little bit into the distal taper, we're getting close. But at the tip all the way up to the full distal taper on that knife was fully case hardened. Like I said, the tip was well over 1% carbon. It was probably closer to 1.5% carbon, getting pretty close to over carburizing it to cast iron. Here's a tooth cutter for like a gear. You see the case hardening comes in, but this tip here, this body still got iron in it, but this tip, it's fully case hardened. If you were going to try and through harden this whole thing, you'd end up with cast iron on the tip. The first time you spun it up and it touched a piece of metal, this tip would explode or break off. Okay, now we're going to talk about carbon migration in a mono piece of steel. We case hardened it. Now we've got it in the fire to even out the case harden, the carbon content. We're going to think about it as it happening in waves. The carbon's just going to crawl in from all sides, a little wave at a time, like the waves on the beach, tide coming in. This diagram down here is going to represent the carbon content as you etch it. You etched it and it's super dark. And the inside, low carbon, light. We let it sit for a while, we bring it back out, polish it, etch it. Light, so the center's still light, and the hard part has now changed color. It's gotten lighter because it's distributing the carbon, and the average carbon content is going up, away from the extreme, becoming normal. And this last one, it's migrated all the way through, and it's all one solid color, all one even carbon content. Now doing it this way usually requires thermocycling at very high heat. The one I did on my knife was, that tang was 3/16 of an inch. And I brought it up to a welding temperature once, let it cool all the way down to a black heat where I could touch it. Did that again, and that wound me up here. Before I thermocycled it, it was here. The first time put me somewhere here, and the last time I had an even carbon content. Talk about carbon migration in Damascus and the creation of shear steel. Like I said in the other video, shear steel is made by case hardening a bunch of pieces, forge welding them together into a new bar, and that would even out the carbon content. And the carbon content would stay high because if you look, you have double the amount of case hardened material at the weld seam than the iron interior. So the carbon doesn't have much distance to travel, and it doesn't have much to make up. So you lose very little in the way of carbon percentage. And as far as Damascus goes, black splotches in your pattern are a phenomena, and there's no real good way to explain them, but the disparity comes from how great the difference is in carbon contents of your metals. So the further away they are on the spectrum, the higher likelihood of you getting a little bit of carbon migration and black splotching in your pattern. Is it a guarantee? No. Can it happen? Yes. Why does it happen? I'm not a metallurgist. Now let's talk containers. A container doesn't need to be sealed, super airtight. It just has to prevent enough oxygen from getting in to combust your materials during the heat up and the cool down phase. Now we don't really have to worry about the phase in the middle during case hardening because of the chemical reactions displacing oxygen or consuming the oxygen. A good way to test if your container is going to be good for case hardening is making charcoal in it from wood or char cloth from an all cotton piece of clothing or a rag. I said, I like using these threaded pipes. The gases and air vent out of the looseness of the threads, and due to my inattention and inexperience, the split that happened in this. But my char cloth container is a perfect example of this. This is an Altoids tin. Usually you'll see people put a hole in the top. It's completely unnecessary because there's already a few holes in the back where the metal is cut out and folded to make the hinge, and it displaces the air and the gases inside and pushes them out of these lips, and the flames curl up and away. Now, during the cool down, because the gas has to do some fancy stuff to get inside, it takes a lot longer, and it prevents that oxygen from getting to this char cloth and burning it up before it's cooled down past the burning temperature. Now, I should probably explain pyrolysis, which is the process of turning wood or any organic material into carbon. So basically, we're going to take all our cloth or wood, raw wood, put it in this container, and we're going to put it in the fire. The fire is going to indirectly heat these materials until they hit their combustion temperatures, at which point they will burn inside this container and drive off all the volatiles, impurities, and that will come out in the form of smoke and flame. Once that smoke or flame stops, pyrolysis has completed, and you remove this container from the fire and let it cool down. And when you open it up, what you should be left with, if you had a container that was airtight enough to stop oxygen from getting in here and continuing the combustion process, is a piece of almost pure carbon material.